Hello everyone, I will present our work entitled Weekly Supervised Learn Guide by Activation Mapping Applied to a Novel Citrus Pest Benchmark. My name is Edson, Elio and Sandra are the co-authors of the paper. We are from University of Campinas, Brazil. Our main motivation is the automation of integrated pest management, the IPM process, for citrus, where inspectors go to the orchards using their magnifying glasses to look for mites and insect pests. Insects and mites are usually very small compared to the whole image, just like the dot in the image on the right side. Believe it's a mite. As an example, this video shows how difficult it is to track mites with magnifying glasses. It's a red spider mite running on citrus leaves. As we can see, the detection of mites is a very challenging task. To tackle this challenge, we propose the use of mobile device coupled with magnifying glasses to collect a new benchmark of mites. In addition, salience maps are used to highlight the mites for a weekly supervised multiple instance learn method. Here we can see some samples for our image collection called Citrus Pest Benchmark or CPB. The CPB dataset contains around 10,000 images. To collect the data, we carry out scheduled inspections in the production unit areas. The inspectors choose samples from the crop lines not near the border to analyze the fruits, new germinations and stings. They use it to collect from every 13th plant individual in a line and examine every 3 planting lines. We used the samples visited by the inspectors to obtain the mite images. The CPB was divided into 7 categories, 6 mite classes and the negative class. In addition, as most works in the literature, we divided the CPB into 3 sets called training, validation and testing, which contain approximately 60%, 20% and 20% of the images, respectively. The second contribution of our work is the development of a weekly supervised multiple instance learn method guided by salience maps. The first step of the process is to train a CNN model pre-trained on the ImageNet that we call bag model. After, we use the bag model to produce a salience map, which will serve as an input to our Patch-SaliMap. The Patch-SaliMap uses the salience maps to select patches with a size smaller than the original image to train a new model in step 3. Also, in step 3, we used the patches produced to train a new model using the old bag model, which we call the instance model. Finally, we used the weight evaluation method to evaluate the inference for the original image using instances. New methods usually need to change loss or pooling layers to be performed because the instances have no labels. In our process, we have not changed anything in the CNN architecture. Therefore, we can say that our process decreased the chance of training with wrong labels, creating almost a supervised mill method. We used the gradient to create the salience maps. These salience maps are activation maps and, due to this peculiarity, our method is guided by an activation map. Here we can see the highlight areas and the paths chosen from them. Regions of interest in the original image have different proportions. In the instance, the mite regions are proportionally larger in relation to the entire image, and in relation to the original image also. To choose the most suitable architecture for our mill method, we use the validation set from the IP102, and we found the efficient net as the best accuracy outcome in relation to the number of parameters. Then we compared the results of efficient net to the literature using the test sets. We improved the state of the art on the IP102 dataset with a model with fewer parameters. For the CPB, we compared the empirical results for the binary task of mite classification, where the task was to decide whether or not the mites were in the images. As we can see, the results trained in the original image were worse than the patch-based results. Among the results for the patch-based approach, those produced automatically achieved the best performance. Here we can see the difference between the grid created and the patches noted manually, as well the patches created and annotated automatically by our method. We evaluate the use of different sizes for patches generated manually and automatically to make proportional regions comparable. Concluding, as main contributions, we collected a citrus pest benchmark using mobile devices coupled with magnifying glasses, created a weakly supervised multiple instance learning method guided by activation maps, developed a weight evaluation strategy for the instance, and achieved promising classification results on CPB and IP102 datasets, including an accuracy rate of 92.1% in the binary classification task on CPB. Thank you very much for your attention.